Let us define the composition of two relations. Suppose that R is a relation from a set A to a set B, and S is a relation from B to a set C. That means R is a subset of A cross B and S is a subset of B cross C. Suppose we are having two such relations. Now we can define a relation S composition R. There is a subset of A cross C. That means S composition R is a relation from A to C defined as follows. That is, S composition R is the set of all ordered pairs X, Z in A cross C such that there exists an element Y in B such that XY is an element of R and YZ is an element of S. In that case, this is called the composition of the relations Rness. Some people are denoting the same thing by this symbol, but we are not following that notation. we are always using the notation S composition of S. Recall that we had defined the inverse of a relation in the last class. That is, if R is a relation from A to B, we had the relation R inverse from B to A defined by R inverse is a set of all XY in B cross A such that XY belongs to R. This is the definition of the inverse of the, or inverse or converse or reverse of the relation R. Now, what is the reverse of the composition of two relations? That is, what is the inverse of this? You can see that this is equal to R inverse composition S inverse. Note that R is a relation from A to B. Therefore, R inverse will be a relation from B to A, and S inverse, S is a relation from B to C. Therefore, S inverse will be a relation from C to B. Therefore, R inverse composition S inverse will be a relation from where to where? From C to A. And S is R is a relation from A to B and S is a relation from B to C, means S composition R is a relation from A to C. Therefore, S composition R inverse will be a relation from C to A. So here S composition R inverse as well as R inverse composition S inverse are relations from C to A. So the question is whether they are the same or not. When two relations are one and the same, if and only if they contain the same elements, the same ordered place. You can see that these two relations are one and the same as follows. That is an ordered pair Zx belongs to S composition R inverse. Here Z belongs to C and X belongs to A. This happens if and only if XZ belongs to S composition R by the definition of the inverse. And this happens if and only if, by the definition of the composition, if and only if there exists a Y in B such that XY belongs to R and YZ belongs to S. And this happens if and only if XY belongs to R is equivalent to saying that YX belongs to R inverse and YZ belongs to S is equivalent to saying that ZY belongs to S inverse. And these two things happen if and only if ZY belongs to S inverse and YX belongs to R inverse if and only if ZX belongs to R inverse composition S inverse. So we have that Zx belongs to S composition R inverse if and only if Zx belongs to R inverse composition S inverse. That means S composition R inverse and R inverse composition S inverse contain the same elements or they are equal. That is, the S composition R inverse is the same as R inverse composition S inverse. Suppose f and g are two functions from A to B. F is a function from A to B function and g is a function from A to B. Then when do we say that f is equal to g? F and g are two functions means they are two relations, means they are sets, and two sets are equal if and only if they contain the same elements. So two f and g are equal if and only if they contain the same ordered pairs. So actually there is no need of giving a separate definition of the equality of functions, but in this context it's more convenient to have a definition for the equality of two functions. That is as follows. There is f from A to B and g from B to from A to B, then f is equal to g if and only if f of x is equal to g of x for every x. That is, two functions f and g from S at A to S at B are equal if and only if f of x is the same as g of x for every x in. This is the definition of equality of functions. Actually, this is a consequence of our original definition of equality of two sets. So there is, this is not nothing new, but this formulation is convenient when we deal with functions. That is, two functions are equal if they have the same domain and codomain, and at each of the values, at each of the elements of the domain, the value of both the functions are one and the same. That is the equality of functions. I would like to the properties of that. Similar to that, we can define the preimage of a set also. Suppose f is a function from, say, x to y. Let b be a subset of y. Then we can define f inverse of b as the set of all x in set of all x in x such that f of x is an element of B. X is f is a function from a set x to a set y, and B is a subset of y, the codomain. For that subset of the codomain, we are defining f inverse of B as follows. F inverse of B is the set of all elements small x of capital X such that f of x, the image is an element of. This is called this f inverse of B, this set is called the pre-image or the inverse image of B under F. Sometimes called inverse image. So f inverse of B is the inverse image of B. Now what will be the inverse image of y? There will be x, clearly. And what will be the inverse image of the empty set? Clearly, the empty set. And we can also see that if B1 is a subset of B2 is a subset of y, then f inverse of B1 is a subset of f inverse of B2. Is obvious. Then we can ask a question. If A is a subset of B, A is a subset of y and B is a subset of y, then what is f inverse of A union B? That will be equal to f inverse of A union f inverse of B. That is, the inverse image of a union is the union of the inverse images. How to prove this? Can be proved as follows. X belongs to f inverse of A union B if and only if f of x belongs to A union B. This happens if and only if f of x is an element of A or f of x is an element of B, and f of x is an element of A if and only if x is an element of f inverse of A. F inverse is f of x is an element of B if and only if x is an element of f inverse of B, and this happens if and only if x belongs to f inverse of A union f inverse of B. That means f inverse of A union B is equal to f inverse of A union f inverse of B for every subset A and B of y. So the inverse image of a union is the union of the inverse images. Similarly, we have that f inverse of A intersection B is equal to f inverse of B intersection f inverse of A intersection f inverse of B also in the same context. In the case of, that is, inverse image of an intersection is the intersection of the inverse images. In the case of images, the second result was true. That is, for images, image of an intersection is not necessarily equal to the intersection of the images. But for pre-images, no problem. Pre-image of a or inverse image of a intersection is the intersection of the inverse images. How to prove this? Proof is easy. X belongs to f inverse of A intersection B if and only if f of x belongs to A intersection B if and only if f of x belongs to A and f of x belongs to B if and only if x belongs to f inverse of A and x belongs to f inverse of B. This happens if and only if x belongs to f inverse of A intersection f inverse of B. So f inverse of A intersection B is equal to f inverse of A intersection f inverse of B. So inverse image of an intersection is the intersection of the inverse images. Intersection of a union is the union of the inverse images. Moreover, you can see that inverse image of a complement is the complement of the inverse images also. That is, if A is a subset of Y, we can see that f inverse of A complement is the complement of the f in. Preimage of a complement is the complement of the preimage. This is proved as follows. There is x belongs to f inverse of A complement if and only if f of x belongs to A complement. F of x belongs to A complement if and only if f of x is not an element of A. And this happens if and only if x is not an element of f inverse of A. And that happens if and only if x is an element of f inverse of A. There is one problem. Here A complements means y minus A. And here f inverse of A complement, that means x minus f inverse A. So, can also put it like this, f inverse of y minus A is equal to x minus f inverse of for every f is a function from x to y and A is a subset of y. The inverse image of a complement is the complement of the inverse image. So note that this inverse behaves very nicely. Inverse of a union is the union of the inverses. Inverse of an intersection is the intersection of the inverses. Inverse of a complement is the complement of the inverse. But the image is not behaving that nicely. Even though one property is written, the image of a union is the union of the images. But image of an intersection need not be the intersection of the images. And for complements also that result is. But of course for one-one functions we had that the image of an intersection is the intersection of the images. But here for the inverse image all these properties hold for any function. Now suppose f is a function from x to y, and suppose y is an element of y. Then we have a notation f inverse of y is the set of all x element of x such that f of x is equal to y. That is, if you take an element in the codomain, the preimage of that element means the set of all elements of x which are mapped to that element. This is nothing but f inverse of singleton y, which is already defined, because f inverse was defined only for sets earlier, but sometimes it is convenient to define the inverse image of an element also. That is the same as the inverse image of the corresponding singleton set. Not that this set need not be non-empty always. If the function is not surjective, sometimes this f inverse of an element can be empty set also. And if the function is not 1, not injective, the f inverse of a particular element may contain more than one element. But sometimes this notation is useful. Not that this notation we can use even when the inverse of the function does not exist. Here f is just a function from x to y. I am not assuming that it is a bijective function. Since this is not a bijective function, f inverse may not exist as a function. But this notation is and there is convenience sometimes. But just because we use this notation, that doesn't mean that f inverse is a function, because actually f inverse of a particular element is a set, not an element. But if f is a bijection, this f inverse of y will be a singleton set always. And in that case, f inverse is a function, and therefore we can take f inverse of y as an element also, because precisely that f inverse of y will be a singleton set. F inverse of y will be a singleton x. But sometimes we may even write f inverse of y is equal to x if f of x is equal to y, and f is a bijection. But in the case of function which is not necessarily bijective, this notation is sometimes useful. Some people call this the fiber. Some people call this fiber. When we defined union, intersection, etc., I was considering only unions of two sets, intersections of two sets, A and B. But we have seen that both the operations of union and intersection are associative and commutative. That is, A union B is the same as B union A, and A union B union C is the same as A union B union C. And similar results for intersection also. That is, A intersection B is the same as B intersection A, and A intersection B intersection C is the same as A intersection B intersection C. That is, both the union and intersection operations are commutative and also associative. Because of that, we can even consider A union B union C. Whether you bracket this way or that way, that is immaterial. And you can also consider A union B union C union D, etc. And how the brackets are put is immaterial. You can put in any way you like. So you can write in just like this. Or you can consider this as the union of the sets A, B, C and D. Then we can think of the union of a collection of sets. Suppose you are given a collection of sets. You can define the so by this so now we are having the union of 2 sets, 3 sets, 4 sets. Still by induction we can go up to union of a finite number of sets by applying this operation again and again. But we need not stop there. You can even have union of an arbitrary collection of sets. Suppose that is, we can have a collection of sets. So a collection of sets means this set. A set of sets, sets of sets of sets, and just for the beauty of that, we, for aesthetic purpose, we will sometimes say instead of sets of sets, we say collection of sets, or sometimes we say class of sets, or we say family of classes of sets instead of writing sets of sets of sets, etc. So sometimes we use synonyms like collection or family or class. So suppose C is a let C be a collection of sets. Then we can define the union of that collection of sets as the set of all X such that there exists a capital C in script C such that X is an element of capital C. That is, the union of a collection of sets is the set of all objects which belongs to some set in that collection. So this is, so thus the union is defined for all collections, whether your collection is finite, countable or even uncountable, or this is for an arbitrary collection, that is an arbitrary collection. Arbitrary collection means that collection can be finite, that collection can be empty, that collection can be non-empty, the collection can be countable, the collection can be finite, the collection can be uncountable. Whatever be the collection, we don't care. So if C is any collection of sets, we can define the union of that collection of sets as the set of all objects which belongs to some set in that collection. This is the condition. So union, the concept of union can be generalized. If this collection C is just a collection containing only two sets A and B, then union C is A union C. So this is a generalization of our previous definition of union of two sets. Now what happens when the collection is a singleton collection with only one set? Then union C is just A. So if you are having a collection of just one set, the union means that set. Now what if script C is an empty collection of sets? Then how will you define union? We define this union as the empty set. Why? How can that union be non-empty? If that union is to be non-empty, there should exist some object which is an element of some set of the empty collection. There cannot be any set in the empty collection. Therefore, such a thing cannot exist. Therefore, the union of the empty collection is empty. Or union of the empty collection is, so empty union is empty. So union of an empty collection is empty. Some people may have some discomfort about this concept. Some people are not very comfortable with this idea. But of course I don't have problem. Many people don't have problem. In several textbooks, the union of the empty collection is taken as the empty set. Then there arises a question: what is the intersection of? We can also define intersection of a collection of sets. Suppose let script C is be a collection of sets, or a class of sets. Then how to define it, the intersection of that? We can define it as the set of all objects X such that X belongs to A for every A in that collection. There is given a collection of sets, the intersection of that collection is the set of all objects which belongs to every set in that collection. That is the definition. If your collection contains only two sets A and B, then intersection C is A intersection B. And when your collection C contains only one set A, intersection C is taken as A. But the question is, what is this when C is an empty collection of sets? That is, what is the intersection of the empty collection of sets? Here, there is a problem. What are the elements which belongs to every set in the empty collection? Now, suppose that X is not an element of this intersection. Suppose I want to prove that some object is not in this intersection. How is that accomplished? This happens if and only if there exists a set A in the empty collection such that X is not an element of A. This intersection in the empty collection is the set of all objects which belongs to every set in the empty collection. If X is not in the empty collection means, in the intersection of the empty collection means, there should exist some set in that empty collection which doesn't contain X. Is it possible? This is not possible. This is not possible. Why? Because empty set cannot contain any set. So this is always false. This is always false means this is always false. That is, an object is not in the intersection of empty set is always false. Which Then the only possibility is that everything belongs to the intersection of the empty collection. Then that intersection of the empty collection will be a set consisting of everything, and it will lead to big philosophical problems. You cannot consider a set of everything. A set of everything cannot be considered. But in some special contexts, we may have a universal set or a master set. In that case, every object in the master set will be in the intersection. And some people will take a notion that the intersection of the empty collection is the universal set or master set. If a universal set or master set exists in your discussion, but in set theory, if you take set theory is the study of all sets. So what will be the master set? If there is a master set, every set should be a subset of that set. Such a set does not exist in set theory. We'll come to Russell's paradox. Then that will be clear. Russell's paradox, that will be clear, because we cannot. Russell's paradox means you cannot have a set containing every set of all sets. Such a set not. So if you are working with subsets only of a particular set, suppose we are working in number theory. Number theory means the study of positive integers. Then in that case we can take a feeling that take an idea that every set considered in our discussion are subsets of the set of positive integers. Or when we study real analysis, we can take a view that every set considered are subsets of the real number, set of all real numbers. So that means there is a master set or a universal set. And in such context, we can say that empty intersection is that master set or the universal set. But if there is no master set or universal set, the empty intersection is not defined. So this is a bit controversial. But regarding the empty union, there is no confusion. Empty union is always taken as the empty set. But empty intersection definition will create some problems. And some people define the empty intersection as the universal set or master set if there is a universal set or master set in your particular discussion. So that is a bit controversial. So we can take a stand that if you take any non-empty collection of sets, the intersection is defined. Whereas in the case of union, for an arbitrary collection of sets, we can take the union. That is the stand we can take.